afternoon. I am Alishia Reynolds, and my research topic for this program for the REU is solutions of general heptagonal reduced equation. I will be working with Dr. Mohammed Kareem. He's the chairperson of the math department here at AAMU.
What's the arrow keys?
Put the how bad.
Okay. Over the years, we have mathematicians that have tried to formulate formulas to solve high-order polynomial equations. They have, Gales in 1978 proved that there is no particular formula to solve equations of x f to the fifth or higher degree order. So what we're trying to do now is formulate a solution to go ahead and solve those high-ordered polynomial equations. We know from so far that we can use the quadratic formula, cubic formula, and the quartic formula so far to solve x to the cubed and x squared and x to the fourth, but we have yet to find those solutions for x to the fifth. So what Mohammed Kareem has done in the math department is he has gone ahead and figured a way to solve equations of degree 5 and higher. So we know when we're solving x cubed and x fourth equation, we would just use the general formulas that they have, the cubic and the quadratic, in the quartic equations, and put it into the respective formulas, and bam, the solution is solved, and there's no more need to do that. So what do we do when we need to solve for solutions of degree 5 and higher? From the quartic formula, we've proven that if we use the Unipodal number system, and what that is if you take a number w and its standard basis set 1 and u, we'll let w equal w naught plus u1, where u squared equals 1, but u does not equal plus or minus 1. If you look at that, it kind of puts you along the line of the imaginary number I. But we can't really call it that because of the simple fact that the imaginary number I is always going to equal 1. But in this case, where u is not going to be able to equal plus or minus 1. So we're going to let w naught and w1 be complex numbers. And the basis u and u is defined as u equals 1/2, 1 plus u, and u equals 1/2, 1 minus u, plus or minus, because in most polynomial equations you have a plus y minus b plus y, so we need to account for the plus and minus. And we also know from the idempotent basic and binomial theorem, we can take that w plus, u plus, and w minus, u minus. This is actually supposed to be a plus on here. Sorry about that. We know that if the idempotent theory states that if we expand the equation raised to any power, it doesn't change it. So as you know, if we go ahead and we expand it out like the binomial theorem and the powers, it's still going to leave us with the general equation intact without changing the solution of it. And we're also going to reduce all this, and we're just going to let it all equal to r. W raised to the n power, which is going to be a high order odd power, equal r. So now that we know the Unipodal equation of Wn equal r, we're going to say that the r set equals r equals s plus u of t, where u is being identified as a imaginary number for complex numbers. And we're going to use the standard basis x plus yu n in the place of w equals s plus tu. We're doing this so once we start to break down the polynomial equation, we will have our complex number set along with our imaginary set. So what am I saying? Let's consider here a reduced heptagonal equation: x raised to the 7 plus 7 ax to the 5th plus bx cubed plus cx plus d equals 0. From the idempotent and the binomial theorem breakdown, we have x plus y to the u raised to the odd power 7 equals s plus tu. So once you do once you apply the binomial theorem, you will get x to the 7 plus 21x to the 5th y squared plus 35x cubed y to the 4th plus 7x y to the 6th plus 7x to the 6y plus 35x to the 4th y cubed plus 21x squared y to the 5th plus y to the 7th equals s plus u of t. From here we know that we are able to separate our complex scalar part, which will be the very first part without the imaginary u, that we're considering it to be an imaginary number. We have x raised to the 7 plus 21x to the 5th y squared plus 31x cubed y to the 4th plus 7x y to the 6th minus s equal 0. And from there, we will do a basic expansion. What we're doing here in the next step that is to come, that I already have worked out before I create this slideshow, is from there, from the previous equation where you have x to the 5th y squared, you will now be trying to substitute, break down and manipulate the equation to have it reduced to x squared minus y squared. So from here, so you have x to the 5th y squared. So now we want to manipulate the equation to like x to the 7 plus 21x parentheses, well, x cubed parentheses x squared minus y squared. We want to manipulate and break down the equation. And we do that in an attempt to expand it. That way we can go back and imply because this x squared and y squared is now going to be called rho. We wanted to get it into a rho equation. And that is the end so far.